morning, students. I'm Chaitanya, Assistant Professor in Mathematics, working in Institute of Aeronautical Engineering, located at Dundigal, Hyderabad. Today, we are going to discuss about some key elements of exponential distribution, that is, derivation of mean, derivation of variance, and some applications of exponential distribution in finding real-time probabilities. So, as a part of our curriculum, probabilistic modeling and reasoning, we are in the module 2 and we are going to discuss the topic mean and variance of exponential distribution and applications. Let us look into the things one by one. So first let us recap what is moment generating function, because we are also going to derive the moment generating function of exponential distribution. Okay, so moment generating function, you know the definition of a random variable capital X. The moment generating function is defined as mx of t is equal to expectation of e power tx. And you can write e power tx as 1 plus tx by 1 factorial plus t square x square by 2 factorial plus t cube x cube by 3 factorial, and so on. And by applying expectation to each and every component, we'll get 1 plus t by 1 factorial into e of x plus t square by 2 factorial into e of x square plus t cube by 3 factorial into e of x cube, and so on. Here we call this e of x as moment and first moment, and e of x square as second moment mu2, and e of x cube as third moment mu3, and so on. So every moment mu r can be written as e of x power r. Okay, and that is what we have discussed in the last class. Now, that is just now we have seen the expansion, and mu1 expectation of x, mu2 expectation of x square, mu k expectation of x k, and these are called moments. And also you can directly derive a moment mu k directly from the moment generating function by differentiating the moment generating function for k times with respect to t and substituting t is equal to 0. So by differentiating the moment generating function m of t with respect to t for k times and substituting t is equal to 0, you will directly get the mu k value. So mu1 will be the first derivative of m of t with respect to t and t is equal to 0. The mu2 will be the second derivative of m of t with respect to t and t is 0. Like that, we can directly derive the moments with the differentiation of the moment generating function and substituting the t is equal to 0. And let us recap the definition of density function of exponential distribution. See, exponential distribution is a continuous random variate. In fact, it is a random variate which assumes time. Time is a continuous flow. It never breaks. So time is always a continuous random variable. So the exponential distribution follows the density function f of x given by lambda into e power minus lambda x, where x is always greater than 0. That is, time is always non-negative, that is positive, and hence the density function of exponential distribution is given by f of x lambda into e power minus lambda x. So the output under exponential is given by, that is f of t, will be lambda into e power minus lambda t. If you assume that f of t is the velocity of a satellite launched into the space, then f of t will be some lambda into e power minus lambda t. That means f of 1 gives you, if you assume that t is seconds, f of 1 gives you the velocity of the launched vehicle as lambda into e power minus lambda. And at the second after 2 seconds, it will reach the velocity of lambda into e power minus 2 lambda. So this is called exponential distribution. So exponential distribution nothing but whose density function is given by lambda into e power minus lambda t, where t is time, that is non. Okay, and also we are going to derive the distributive function, that is capital F of x. Why? What is the difference between small f of x and capital F of x? First, let us know. Small f of x is a density function which helps you to calculate a probability point-wise. Whereas this is cumulative probability calculator. That is, we can calculate this function is given by, of course, we are going to derive it, 1 minus e power minus lambda x. Here, if f of 3 gives you the velocity of the launched vehicle at third second, capital F of 3 gives you the cumulative velocity of the vehicle until 3 seconds, that is up to 3 seconds. First 3 seconds, how much velocity it has accumulated. And this is exact velocity at third second. This is point wise, this is cumulative. Okay, like that, you can differentiate. How to derive capital F of x? Capital F of x, by the definition, will be like this. P of capital X less than or equal to x. And its definition tells you that integration of 0 to x f of x dx. And you know, it is integral 0 to x lambda into e power minus lambda x dx. Automatically, the integration becomes e power minus lambda x by minus lambda under the limits 0 to x. And hence, you will get 1 minus e power minus lambda x. So, it is a simple derivation. Capital F of x is a simple derivation from the small f of x. Small f of x helps you to calculate the probabilities pointwise. What is the chance of happening of an event in the first minute is given by small f of n. What is the chance of happening of an event at 10th minute is given by f of 10. What is the chance of happening of an event at 100th minute is given by f of 100. Whereas, what is the chance of happening an event within first 10 minutes is given by capital F of 10. That means it accumulates the probabilities f of 10. And what is the chance of happening an event within first 100 minutes, that is given by f of 100. This is at 100th minute. It is within 100 minutes, within first 100 minutes. Please understand the difference. At 100 minutes, within 100 minutes. That is the difference between small and capital. Okay, now let us summarize these things. So, the density function is given by f of x for exponential distribution lambda into e power minus lambda x, x non-negative. And the distributive function is given by 1 minus e power minus lambda x, x greater than or equal to 0. And moment generating function definition also we have seen. Now, just the summary of cumulative distribution function, saying that it is when it is non-negative, the value will be this, and negative it would exist as time is always positive. Let us try to derive the mean of exponential distribution first. Okay, we are going to derive the mean of exponential distribution in two ways. One is direct derivation, and the second way is through moment generating function. The first way, that is, mean means expectation. You know very well. Mean has several synonyms: expectation, average. Okay, all these are synonyms of mean. So expectation of x, where x is an exponential variable. So it is integral minus infinity to infinity x into small f of x dx, where small f of x is the density function of exponential distribution that is given by lambda into e power minus lambda x. So this becomes minus infinity to infinity x into lambda into e power minus lambda x dx. Now, By keeping the constant outside the integral, we'll get lambda gets outside, and hence x into e power minus lambda x. Now you see, this integrand is a product of two functions where first one is polynomial and the second one is some other function other than polynomial. So when you have the situation of product of polynomial into another function, that is polynomial into something, you will apply Leibniz rule. So to find the to integrate a function as a product of polynomial into some other polynomial into something, we'll apply Leibniz rule. Okay. Now here polynomial is fixed for differentiation and the next function is fixed for integration. According to Leibniz rule, we have to fix the polynomial for differentiation and the next function for integration. Now, how the Leibniz rule works? Let us see. Now check. What is the degree of polynomial? Our polynomial is x. What is the degree of polynomial? X power 1. So degree is 1. Let us increase 1 to one more step, that is 2. That means when the polynomial is of degree 1, we have to take 2 symbols. When the polynomial is of degree 2, we have to take 3 symbols. When the polynomial is of degree 5, we have to take 6 symbols. So every time we will take 1 symbol extra than the degree. That is why we are going to write here like this, lambda into 2 symbols, because polynomial x is of degree 1, we will take 2 symbols, plus and minus. And each symbol should be accompanied with 2 brackets, one for derivative, one for integral. One for derivative, one for integral. Okay, and the limits are as usual minus infinity to infinity. But here we have to remember that f of x is x non-negative. The limits become 0 to infinity, and hence we can take 0 to infinity. Okay, so the limit becomes 0 to infinity by the definition of density function of exponential distribution, 0 to infinity. Now, here we already said that this is for derivative, this is for integration, this is for derivative, this is for integration. What is fixed for differentiation? Polynomial. So x is fixed for derivative. Let us copy it here into the first bracket. X derivative 1, 1's derivative 0. So that means we will copy the polynomial into the first bracket. Its derivative, its derivative, its derivative, like that will go. Okay, so x derivative 1. Now, what is fixed for integration? E power minus lambda x. You know, the integration of e power ax is e power ax by a. In that way, e power minus lambda x, when integrated, it becomes e power minus lambda x by minus lambda. And second integral, that means 2 times if you integrate, it becomes e power minus lambda x by minus lambda whole square. Okay, this is called Leibniz rule. Leibniz rule is nothing but a short way of expressing the byproduct rule, the product of biparts. Okay, the integration of biparts. So this way we can write. Now let us substitute the limits. That means we are going to substitute the upper limit infinity minus the lower limit 0 into the values, x value. When you substitute upper limit here, you have to remember few important formulas. That is, you know what? E power 0 is always 1. You know, anything power 0 is 1. But what is e power infinity? E power infinity is always infinity, because e power x is always an increasing function, and it has unbounded. E power infinity is always infinity, and e power minus infinity will be 0, because it is reciprocal of e power. Okay, so you have to remember these things as follows: e power 0 1, e power infinity infinity, e power minus infinity 0. So let us substitute infinity here. E power minus infinity 0 minus e power minus infinity 0. E power minus infinity 0, e power minus infinity 0 by substituting x is equal to infinity. By substituting x is equal to 0, we get 0, okay, 0 into 1 by lambda. So 1 by minus lambda. And by substituting 0 here, we get 1 by lambda square. So finally, what we get? Lambda by lambda square. And the answer is 1 by lambda. So we started with expectation, the definition. According to the f of x limits, it becomes 0 to infinity. Integration by parts or Leibniz rule. Substituting infinity, substituting 0, upper limit and lower limit, we get 1 by lambda as the answer. So by summarizing these things, we have proven that E of x is equal to 1 by lambda, which is an important formula where expectation for the function exponential distribution lambda into e power minus lambda x. The mean is 1 by lambda. That is what we have derived. Next, we are going to find the variance of exponential distribution. Before that, I'd like to explain same set derivation with the help of moment generating function. After a few seconds, we'll derive the moment generating function and we'll cross check the same mean whether we obtain the with the help of MGF or not. Okay, now we are going to find the variance of exponential distribution. So variance means we have to start with the formula V of x is equal to E of x square minus E of x whole square. Fine. But already just now we derived that E of x is 1 by lambda. So this becomes E of x square minus 1 by lambda square by substituting the value. Now let us separately derive let us name this as equation star and let us derive E of x square. According to the definition, minus infinity to infinity x square f of x dx. But exponential distribution means 0 to infinity x square lambda into e power minus lambda x dx. And lambda being constant, it can be sent out, so it becomes 0 to infinity x square e power minus lambda x. Again, we have arrived at the step that the integrand is product of polynomial and exponential. So polynomial into exponential means we have to apply Leibniz rule. Okay, so according to Leibniz rule, what is the degree of polynomial? Please check. What is the degree of polynomial? Degree of polynomial is 2. 2 means we have to take 3 symbols. 2 plus 1. 3 symbols. Okay. So by taking 3 symbols, we'll write the step lambda into plus minus plus. Okay. Limits are 0 to plus minus plus. Each symbol should be accompanied with 2 brackets. One for derivative, one for integration. One for derivative, one for integration. One for derivative and the one for integration. Now x square is fixed for derivative. Exponential is fixed for integration. So x square should be copied into the first bracket. X square derivative 2x. 2x derivative 2. Okay. Now integration, here itself we have to start the integration. Integral of e power x, that is e power minus lambda x by minus lambda. Second time integration, e power minus lambda x by minus lambda whole square. Third time integration, e power minus lambda x by minus lambda whole cube. Okay, so this is how we will apply Leibniz rule. After applying Leibniz rule, we will go for limit substitution, that is lambda into, that is equal to lambda into upper limit infinity minus lower limit 0. We are going to substitute. Let us see what happens. If you substitute x is equal to infinity here, x is equal to infinity, what it becomes? It becomes 0. E power minus infinity 0. Similarly, e power minus infinity 0, e power minus 0. So 0 minus 0 plus 0. If you substitute x is equal to 0 here. 0 square, that is 0 into anything 0, 0 into anything 0, plus 2 into e power 0 1, 1 by lambda. So what do we get? We get 2 by lambda square, that is e of x square. So we arrived at e of x square as 2 by lambda square. Now we started with variance. The formula is e of x square minus e of x whole square, and this we obtained that 2 by lambda square, and this we obtained that 1 by lambda square. By subtracting, we will get 1 by lambda square. So finally, we declare that the variance of exponential distribution is 1 by lambda square. So by combining the two results, we get expectation is 1 by lambda for exponential distribution, and the variance is 1 by lambda square, and standard deviation is again 1 by lambda. That means both mean and standard deviation are equal for exponential distribution. Okay, that is what we arrived at. Now we are going to derive. Of course, this is the same thing which I have explained with the help of pen tablets, and here that is explained in the PPT. This is the expectation formula. This is the integration by parts, and finally expectation is 1 by lambda. And similarly, you will get e of x square is 2 by lambda square, and hence variance of x is e of x square minus e of x whole square, that is 1 by lambda square. Now, our intention is to derive the moment generating function for exponential distribution. Okay, so before going to derive, here it is shown in the PPT that the mg of exponential function will be lambda by lambda minus t. Let us see how we are going to derive it. So let us start with the moment generating function of exponential function. According to the definition, it is e of e power tx. That is integral minus infinity to infinity e power tx f of x dx, where f of x is the density function of random variable, that is exponential. Exponential distribution, that means 0 to infinity e power tx lambda into e power minus lambda x dx. Lambda being the constant, you can write it out, that is 0 to infinity e power px into e power minus lambda x dx. Bases are equal. Bases are equal means powers could be added, that is lambda into 0 to infinity e power minus lambda minus t into x dx. You know, integration of e power ax. Here I am going to write the remaining steps. What is integration e power ax? You know, e power ax by a. So integration, if you treat this as a, e power ax, that means lambda into e power minus lambda minus t into x by minus lambda minus t 0 to infinity. 0 to infinity. Okay, so lambda into, if you substitute infinity in this place, it becomes e power minus infinity. E power minus infinity is 0 minus. If you substitute 0, it becomes e power 0 1, that is 1 by minus lambda minus. And hence we get the answer, we get the last answer as lambda by lambda minus t. Okay, lambda by lambda minus t. So finally we have derived that the moment generating function of exponential distribution is lambda by lambda minus t, which is explained in this PPT, lambda by lambda minus t. Now we are going to expand it as a polynomial of t, that is infinite degree polynomial in the powers of t. Let us see how we are expanding. Mx of t lambda by lambda minus t, right? Now I'll take lambda common in the denominator. It becomes 1 minus t by lambda. Isn't it? Do you agree or not? If you take lambda out from the denominator, we will get 1 here, you will get t by lambda. And lambda will be cancelled. So it will be 1 by 1 minus t by lambda. Okay. Now it will be 1 by 1 minus t by lambda. Now let us recap a formula. The formula is 1 by 1 minus x. Can you say what is the formula for 1 by 1 minus x? The formula is 1 plus x square plus x cube, so on, provided mod x less than. So by using this expansion, you can write it as 1 by 1 minus t by lambda as 1 plus t by lambda plus t square by lambda square plus t cube by lambda cube plus t power 4 by lambda 4 plus 2. From this, the quotient of t by 1 factorial, the quotient of t by 1 factorial is mu1. The quotient of t square by 2 factorial is mu2, right? So what do we get from here? From here, we'll observe that. Let me rewrite those things. We got moment generating function, that is 1 by 1 minus t by lambda, that is equal to 1 plus t by lambda plus t square by lambda square plus t cube by lambda cube. So from this we can write mu1 is equal to 1 by lambda, mu2 is equal to 2 factorial by lambda square, that is 2 by lambda square, and mu3 is equal to 3 factorial by lambda cube, that is 6 by lambda, etc. So in general, mu k is equal to k factorial by lambda or k. Now variance, so mean is equal to mu1, that is 1 by lambda, which we derived in previous slides. We have proven mean is 1 by lambda. Again we have cross checked through MGF. And variance is mu2 minus mu1 square, that is 2 by lambda square minus 1 by lambda square. Again it is 1 by lambda square, which is also true. So we have cross-checked our derivations of mean and variance with the help of moment generating functions. Okay, now finally I'd like to discuss some applications related to exponential distribution, with which I'll conclude the lecture. Okay, yeah, this is the problem we are going to discuss now, which is an important application of exponential distribution. The number of days ahead travelers purchase their airline tickets can be modeled by an exponential distribution. I already told you that exponential distribution always helps us to model a distribution which is related to time, timely distribution, that is time related functions will be modeled by exponential distribution. So here, airline ticket booking is always relates to time, depends on time. So that is why exponential distribution acts as a good modeling for airline ticket booking. Okay, and according to the statistics of an airlines like Indigo or Air Deccan or Air India, whatever, some airlines, according to their calculation, the airline ticket booking follows exponential distribution with the average amount of time equal to 15 days. That means on an average for each 15 days they will have one advance booking ticket into a flying from one place to another place, one specified place to another place. Now, basing on this, find the probability that a traveler will purchase a ticket fewer than 10 days in advance. Now, basing on this knowledge, you have to find probability that within 10 days they will receive a booking from a customer. a customer is going to book a ticket within 10 days. Okay, less than 10 days. Less than 10 days. They will receive a booking from a customer. And also, how many days do half of the all travels wait? That means 50% of the travels tickets will be booked within how many days? Okay, within how many days? You'll have half of the uh, flight will be booked. Half of the seats in the flight will be booked. For this, how long it will take? That we have to explain by using exponential distribution. Now, let us try to solve this problem. See, according to the question, it is following exponential distribution and the average amount of time is 15 days. That is why we can write what is the mean of exponential distribution, that is 1 by lambda. 1 by lambda is 10 days. That implies lambda is equal to 1 by 10. That means every day there will be 1 by 10th customer. Okay, 10 days one customer means every day 1 by 10th customer. You can understand it like that. Now, the variance, if you ask to calculate the variance will be 1 by lambda square, that is 10 square 100. Okay, and now we are asked to find a probability that there will be booking within less than 10 days. Within less than 10 days. There are two ways of doing calculation of this thing. One is the help of density function. One is with the help of distributive function. I am going to explain two ways simultaneously. First, I am going to explain it via density function. Density function means 0 to 10, 0 to 10, lambda into e power minus lambda x dx. That is 0 to 10, integral 0 to 10, 1 by 10 e power minus x by 10 dx. That is 1 by 10 e power minus x by 10 by minus 1 by 10, 0 to 10. That is 1 by 10. 1 by 10 means it becomes minus e power minus 1 minus 1. Okay, and if you calculate this, you will get a probability. Okay, you will get a probability that is 1 by 1 minus 1 by. Okay, 1 minus 1 by. That means 1 minus 1 by 2.718. 1 minus 1 by 2.718. Okay, and this gives you the answer, the probability for having a booking within less than 10 days. Okay, in that way we can use density function. Now let us do the same problem with the help of distributive function. F of 10, that is p of x less than or equal to. According to the distributive function, 1 minus e power lambda x, that is 1 minus e power minus lambda 10 days. So, sorry, lambda within 10 days they are saying. So, it is 10. And 1 minus e power minus 1 by 10 into 10, that is 1 minus e power minus 1, that is 1 minus 1 by e. The same answer we are getting, the same answer. So you can calculate the probabilities either by density function or by distributive function. Both will result into the same answer. Okay, now, sorry, here actually 15 we have to take. So 15 days average means lambda is equal to 1 by lambda is equal to 15. Okay, 1 by lambda is equal to 15, and we have to find x less than or equal to 10. Okay, and that is 1 minus e power minus lambda into 10 by density function. Okay, that is 1 minus e power minus 1 by 15, 1 by 15 into 10, that is 1 minus e power minus 2 by 3. This gives you the probability of having a booking within less than 10 days when average booking is 15 days. Okay, now second bit, what is the probability that within X naught days, there will be 50% of the bookings will be over. 50% of the bookings will be over within X naught days. You have to find that X naught. So that means 1 minus e power minus lambda x naught, because we are using distributive function. 1 minus e power minus lambda x naught, this is equal to 0.5. What is lambda? Lambda is 1 by 15. So 1 minus e power minus x naught by 15 is equal to 0.5. That is, e power minus x naught by 15 is equal to 0.5. So minus x naught by 15 is equal to log 0.5. E becomes log, and this will be a negative value, and hence you will get x naught approximately some positive integer, which gives you the minimum number of days within which the maximum number of days within which 50% of the tickets will be booked. In this way, we can apply exponential distribution to sort out real-time probabilities, real-timely distributions. Okay, now I'd like to conclude this class with a small problem. Okay, and I'll finish this in a quick way. Here, we are going to deal with a problem related to a toll plaza. You can understand it as a toll plaza. In the toll plaza, you'll see some queues waiting according to timely. Slowly, one car moves and next car gets in, and it checks out and it moves. So it all related to times and queues. Okay, so exponential distribution will be a correct fit for this kinds of distribution. Suppose that a certain stretch of highway cars pass at an average rate of 5 cars per minute. In this toll plaza, say this is a toll plaza near Hyderabad. For every minute, there will be 5 cars passing through that plaza. So according to their statistics, their records, for every minute there will be 5 cars moving through that plaza. Okay, that is what they have. That means lambda is equal to, you can understand, 1 by 10, or 1 by lambda is equal to 10. 1 by lambda is equal to, 5. 1 by lambda is equal to 5 cars per minute. He is saying 1 by lambda is equal to 5 cars per minute. Okay. Now, basing on this, on average, how many seconds elapse between two successive cars? He's asking in seconds. That means we have to convert the question into seconds. How many seconds elapse between two successive cars? That means between two cars, how much waiting time will be there between two cars, one car and next car? After a car passes by, how long an average will it take for another cars to pass by? Complete one car passes over, then how long another car has to wait? That is what they are asking. How long? You have to find the time. And find the probability that after a car passes by, the next car will pass within next 20 seconds. What is the probability that within 20 seconds there will be another car passing? Find the probability that after a car passes by, the next car will not pass for at least another 50 seconds. So, if you take the question, average rate of 5 cars per minute. So 5 cars per minute per 1 minute on an average. That means 5 cars per 60 seconds on an average. That means 5 by 60 cars per 1 second. Okay, so on an average means mean. Mean of exponential distribution means 1 by lambda is equal to 5 by 60. That is, lambda is equal to 60 by 5. That is equal to 12. Okay, and 1 by lambda is 1 by 12. Okay, now let us go to the problem. So what we have observed, lambda is 12. Okay, now let us solve. So first bit, on an average, how many seconds elapse between two successive cars? Okay, so inter waiting time between two cars we have to find. So lambda is equal to lambda is equal to 12, and 1 by lambda, 1 by lambda is 1 by 12, lambda is 12, right? And let us go to the second question. After a car passes by, how long an average will take for another car to pass by? So we have to find how long means, on an average 12 seconds. It is saying 12 seconds you have to wait for one car. For one car, 12 seconds. Okay, one car passes by. For next car means 12 seconds they have to wait. For second bit, we got the answer 12 seconds. And first bit, on average, how many seconds elapsed between two successive cars? That means first car 12 seconds, next car 12 seconds. They have to wait. So 12 plus 12 means total 24 seconds they have to wait on an average to complete both the cars to get serviced. Okay. And third question, very important. Third question. Find the probability that after a car passes, but the next car will pass within next 20 seconds. That is P of x less than or equal to 20 within 20 seconds. That is 1 minus e power minus lambda x. That is 1 minus e power minus 12 into 20. If you calculate this, you will get the probability that the car will pass within 20 seconds. And finally, he is asking us to find the probability that there will no car will pass at least another 15 seconds. That is x greater than or equal to at least x greater than or equal to 15 seconds. That is 1 minus p of x less than or equal to 15 seconds. That is 1 minus e power minus lambda 15. That is 1 minus e power minus 12 into 15. If you calculate this, you will get the probability that there will be no car at least 15 minutes into the plaza. So this way we can apply exponential distribution to sort out real-time probabilities and to find out the solutions like average waiting time in a queue before toll plaza, average service time, so that there is a need to open another toll gate in the toll plaza, another corridor in the toll plaza. Okay, like that they could plan with the help of exponential distribution. Okay, so with this, I'd like to conclude today's lecture, and in the next class we'll meet another important property of exponential distribution, that is memoryless property and its applications. So I'd like to close now. Thanks for your patience listening. Thank you. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.